Good afternoon. My name is Yuqiong Sun. I am a researcher at Symantec Research Labs. So today I'm going to talk about how do we make security frameworks in Linux kernel available to containers. This is a joint work with David Sefford from GE Global Research, Mimi Zohar, Dimitris Pandarakis, Zhongshu Gu from IBM Research, and my PhD advisor, Dr. Trent Jager, who is ready to answer all difficult questions. So first of all, what is a container? So container is lightweight virtualization that allows you to run multiple isolated Linux systems on a single Linux host. So the biggest difference between container and a virtual machine is that containers share the same kernel. So because of this, containers often sought to offer better resource utilization. For example, they allow faster spin-up time, they allow more dense deployment. So these features are nice for this new serverless computing paradigm, such as Amazon Lambda. But is kernel sharing all good? Well, the answer is obviously no. So the container owners, because the kernel is shared, now the container owners cannot really leverage all these kernel security frameworks that the security community has been building for decades to protect their containers. So for example, they cannot really apply local security policies to govern things like integrity measurements, code execution, mandatory access control, and etc. So I will give you a concrete example using this integrity attestation for containers. And this is a real request from a commercial cloud vendor. So the customer of that container cloud have this request. So they want to be able to attest the integrity of their containers to their customers. So basically, they want to prove to their customers that they only run trusted code, they are not infected by malware, and etc. So this is exactly what the Linux integrity subsystem, aka AppArmor, is designed for. So this is how AppArmor works. So you got a process, it is this system calls like mmap or read or exec, and the kernel, according to some measurement policy, will measure the file to be loaded into the memory, and will record that the measurements into a kernel data structure called measurement list. At the same time, the kernel will extend that measurements to TPM. At a later point, when there is integrity attestation, so the remote verifier will collect the measurements from both the measurement list and the TPM, and it will verify the integrity status of the system. So all this works perfectly for virtual machines or a native Linux host because they all have their own kernel. However, things are broken when it comes to the container world. Why? So because when there are multiple containers running on the system and they share the same kernel, consequently, the measurements from different containers as well as the measurements from the host system are all mixed together in a single data structure inside of the kernel. So you only have one measurement list. And consequently, those containers cannot independently attest their integrity. Second, so even if you can separate this measurement list, say for different containers, you still run into the problem of different policies. So since these are independent container owners on the same host, they might have totally different policies regarding what to measure and what are the good measurements. So for example, let's say a weird researcher like me, I'm saying, I want AppArmor to allow all the vulnerable versions of software. And I would assume that a bank container that shares the same host with me will not be okay with that policy. So, well, in reality, bank will not be happy to work with me, I guess. But you get the gist. So basically, different container owners have their different policies. So they want to be able to independently specify and enforce those policies. So as another example, let's discuss a little bit about mandatory access control for containers. So this is excerpt I took from the Ubuntu RxA documentation. And by the way, RxA is Ubuntu's product container, Ubuntu container product. So it's similar to Docker. So this is excerpt. So what it says is basically programs in a container cannot be further confined. For instance, my circle runs under the container profile, which protects the host, will not be able to enter my circle profile, which protects the container. So I am not a native speaker, but the way that I am translating this is that we can only use AppArmor to protect the container host and all the best for the container. And also, I believe there is some grammar issue with this statement. So the goal of this work is to design security namespace. So basically, we want to figure out, can we virtualize or isolate security frameworks in Linux kernel to make them available to containers, just like how other type of kernel resources are being virtualized or isolated for containers. So ideally, we want to achieve the following functional goals. So first, we want each container to be able to govern the security of its containerized processes. And second, we want each container to be able to independently define its security policies and access its security states. For example, like audit logs, measurement lists, etc. And to satisfy these functional goals, we want to enforce one security invariant, which is a container should not be able to invalidate the security goal of other containers or the container host as expressed via their respective security policies. Well, this is a little bit twisted, but I will summarize it. So basically what it says is essentially a container, so we want to allow containers to independently define and specify their security policy. However, we don't want this to come at the cost of the security of other containers or the host system. So before I can give you a detailed design, I want to discuss a little bit about how other types of kernel resources are virtualized and isolated in the Linux kernel. So this is through a thing called namespace abstraction. So a namespace abstraction essentially wraps a global system resource in an abstraction that makes it appear to the processes within the namespace that they have their own isolated instance of that global resource. So at the time of the paper being written, there was 6 namespaces, and now there are 7. So all of them isolate a specific type of kernel resource. So for example, the mount namespace, it isolates mount points. Essentially, it allows every container to have its own file system hierarchy. And this is how the containers leverage those namespaces to build an isolated container. So we would have a container daemon directly running on the native system, like Docker-D. So upon receiving a request of creating a new container, this container daemon will issue a clone system call with all these namespace flags specified. And then the newly forked process will start running in these new namespaces. It will set up the namespaces, for example, mounting its own root point. And then it will exact the target program. And then the target program starts running in the container in an isolated way. So what we want is actually very simple and very similar to this. What we want is, can we design a kernel abstraction similar to the other resource abstractions, such that when issue a clone system call, we can just give this new flags, and then the newly forked process will start running in this new security namespace, and it will have the freedom to specify and enforce the policy and be protected by IMA, AppArmor, or SELinux, just like if it has its own isolated IMA, AppArmor, or SELinux. So we have this idea. So then we have this, based on this idea, we come up with this initial design. So basically, we were thinking, can we directly virtualize these security frameworks into instances and simply divide the control? So this is how this Strawman design looks like. So basically, we would have, these security frameworks will be virtualized into different instances. And each instance will have its own state and policy. And it will enforce that policy independently. So in this case, we would have a native security namespace for a native system. We would have security namespace 1 and security namespace 2. And we would have the security namespace native govern process P0. Security namespace 1 governs process P1 and P2. And security namespace 2 governs P3. And these 3 different security namespaces will independently apply their security policies and do the enforcement. So clearly, this achieves the functional goal, because now each individual security namespace basically defines its own security. They're all isolated from each other. But do you think it also enforces the security environment that we mentioned before? Do you think that one security namespace might be able to invalidate the security goal of another security namespace? Well, the answer is also yes. So we found two types of attacks against this Strawman design. So the first type, okay, so let's assume that we follow the Strawman design and build this IMA security namespace. So originally, without IMA security namespace, when the program executes some malicious code, that malicious code gets measured, and the measurement was recorded into a measurement list. And later, during integrity attestation, a remote verifier can basically know that the system has run some malicious code and is not of sufficient integrity to use. However, by introducing this IMA namespace following the Strawman design, we now run into a trouble. So the process can fork itself into a new IMA security namespace, and this newly forked process, let's just call it P1. And now the P1 could execute this malicious code. The malicious code still gets measured, but it will be recorded into the measurement list of the namespace 1. So later, after the namespace 1 exits, it basically leaves no footprint on the system. And during the integrity attestation later, a remote verifier will be tricked into believing that the system is of sufficient integrity to use, despite the fact that this malicious code was once executed on the system. So the root reason for this attack is because by doing this Strawman design, we make the kernel security frameworks no longer global. So basically, originally, kernel security frameworks governs all the processes on the system. But now, each instance only governs a subset of those processes. And this introduced this attack. So as another example, let's say we have this one container called container1. It has this precious file that it wants to make it read-only. So he relies on mandatory access control framework to do this. So basically, he specified this policy saying that I want all my processes to be only to read this file, to be only to read this file, but not be able to write to this file. Well, he thinks things are okay, but in reality, what he doesn't know is that this file might be shared with another container, in a way through either file sharing, or it could be through mount binding. So another container, its owner doesn't really know or care what the first container thought about the file. So he can simply specify a policy saying that I want to allow all my processes to read and write to this file. So in this case, this security namespace actually gives a false sense of security to the first owner of this container, because he now believes the file is read-only, but actually it can be arbitrarily written by the second container. So the root cause of this attack is because by doing this naive design, we sort of make the kernel security frameworks no longer mandatory. So instead of having a single system admin to specify the security policy for the whole system, we now have two different parties that can both make security decisions, and sometimes these security decisions conflict with each other. So this actually highlights the challenge that we need to solve in order to design security namespace. So the first challenge is that by design, the kernel security frameworks are global. That means they control all the processes running on the system, and this is actually the requirement to be a reference monitor. However, in the container case, we actually want the container owners to be able to access control over only a limited set of processes. For example, only the processes over its own container. And second, so by design, the kernel security frameworks is mandatory. That means only a single system admin may define security policy. But now, if we want to support containers, so basically we are saying that we want to allow different container owners to make their own security decisions independently. So how to relax these two requirements of the kernel security framework becomes the challenge of designing this secure security namespace. So to solve this problem and address the issue that we incurred in the Strawman design, we rely on two simple insights. The first simple insight is to relax the global requirements of the kernel security framework, we can route an operation to all the security namespaces whose security might be affected by the operation. In other words, even though a security namespace doesn't control all the processes on a system, it is sufficient to only control the processes that may affect its security. The second insight is to relax the mandatory requirements of the kernel security framework. We only allow operation if all the security namespaces that are affected by the operation allow the operation. In other words, even though every container or every security namespace can make independent security decisions, an operation is only allowed if all of them allow that operation. So based on these two simple insights, we built this security namespace design. So this is a high-level overview. So basically, like Strawman Design, we first virtualize the security frameworks into different instances. And each security framework instance will have its own policy and states. So although they share the same kernel code base, but conceptually they are completely isolated, and they will be able to enforce the policy independently. So we added a component called operation router in front of this mediation. So the operation router will route an operation based on which namespace is going to be affected by this operation, and route this operation to all the security namespaces that are affected by the operation. And after each security namespace makes the independent security decision, the security decisions are intersected. Only if all the security decisions allow the operation will the operation be eventually allowed by the system. So as you can see, because different security namespaces make independent security decisions, it's possible that a conflict may happen. So to resolve those conflicts, we designed another component called policy engine that basically analyzes the policy and finds the conflicts at the policy load time. Now let me go into the detailed design of each component. First, operation router. So the key task of the operation router is to route an operation to all the security namespaces whose security might be affected by the operation. But how do we decide whether or not if a security namespace is affected by an operation? So again, we have two simple insights here. First, the operation can often be written as an authorization tuple, where you have the subject, you have the object, and you have the operation itself. And the security namespace often has these implicit assumptions over the subject and object. And based on whether or not those implicit assumptions are violated, we will be able to figure out whether or not a security namespace is affected by an operation. So let's first take a look at the perspective from of the subject. So this is actually the implicit assumption towards subject is actually directly derived from the global requirement of security framework. So basically, a security framework implicitly assumes that it controls all the subjects stemming from the first subject that it sees. For example, for the native system, this means all the processes forked from init. And for a container, this means all the subjects forked from the first container process. So based on this implicit assumption, we can now know how to route an operation from the perspective of subject. So basically, we know that a security namespace might be affected by operation if that subject is associated with that security namespace, or that subject is associated with the descendant of that security namespace. So let's take a look at the previous attack example I showed before. So now, let's say that although this P1, it was forked in a new AppArmor namespace, it executes this malicious code. So because now we consider the subject's perspective of whether or not a namespace might be affected by the operation, we know that the P1 is actually a children of P. So we know that the operation that the P1 runs the malicious code should also affect the security of the native namespace. So in this case, the measurements of the malicious code should not only just be recorded in the measurement list of the security namespace 1, but also the security namespace native. In this way, even after the NS1 exits, later during integrity attestation, a remote verifier can still know the true integrity status of the system. So next, let's take a look from the object's perspective. So the implicit assumption of object is actually directly derived from the mandatory assumption of the security frameworks. So the security framework implicitly assumes that only operations explicitly allowed by the policy can be performed on a system. In other words, all the other operations that were not defined towards an object should never be performed on the system. So based on this implicit assumption, we know that an object may affect the security namespace as long as that object is visible to that security namespace. It doesn't really matter if the subject is invisible. As long as the object is visible, it still may affect the security of that security namespace. So let's take a look at the previous attack example I showed before. So let's assume that we follow this design, and now even though this process from the second container is invisible to the processes of the first container, however, because they share the same file, and the first container really cares about this file, so all these operations from the second container to this file needs to be routed to the first container for mediation in order for the first container to ensure the read-onliness of this file. So by combining this subject's perspective and the object's perspective, we can actually identify which security namespace might be affected by an operation. And then the operation router will route the operation to those security namespaces that are affected by the operation. So after the operation router routes the operation to all these security namespaces, these security namespaces make independent decisions. And then these independent decisions are intersected, and only if all these security namespaces allow this operation, will this operation be eventually allowed by the system. This actually allows us to relax the mandatory assumption of the framework. However, this also causes a problem, which is policy conflicts. So because we will intersect the decisions, this problem may occur. So basically, the operation that is specifically allowed by a container might be eventually denied because some other containers or the host system might deny that operation. This is really hard, or it is impossible to debug because the security namespaces are actually completely isolated. So therefore, we designed this component called policy engine, which could basically detect and inform those potential conflicts at the policy load time. Unfortunately, I won't have time to go into details of this policy engine, but please refer to the paper for the details. So for implementation, we implemented security namespace abstraction for two kernel security frameworks, namely Integrity Management Architecture and AppArmor. So for AppArmor, it is the 1.1 thousand lines of code in C, and it is actually open source. So please check the kernel.org for this code. For AppArmor namespace, it is about 1.5 lines of code in C, and we're working in progress for open sourcing it. So one interesting aspect of the implementation that I want to highlight is that in order to use those security namespaces, it's really straightforward. So we only need to change less than 20 lines of code to the container. Essentially, we're only basically having these two new flags to the clone system call in order for containers to use these security namespaces. So to evaluate this namespace design, we evaluate from two aspects. The first is its effectiveness, and the second is performance. For effectiveness, we measure both the effectiveness of AppArmor and AppArmor namespace, but I'm only showing AppArmor namespace effectiveness here. So if you still remember this expert I took from Ubuntu RxC documentation before, what he says is basically it's impossible to enforce both the host profile that protects the host and the container profile that protects the container at the same time. What we want to show is that by using the AppArmor namespace, it's totally possible. So we took the host profiles we took both the host profile and application profile from the Ubuntu distribution, and we enforced it at the same time. So what we found is that for majority of the applications that are deployed in containers, we can actually simultaneously enforce both profiles with no trouble. There are several, or there are a few applications that we actually cannot enforce both profiles simultaneously. And our policy engine actually yields conflicts for those profiles. For these cases, it's actually the container wants to allow something that the container host denies. So this is interesting, so we dig deeper. What we found is that the reason for these conflicts is often because the proc, the sys, and dev file systems, which are shared between the container and the host operating system. So these file systems are historically being used as interfaces between kernel and user space. So on one hand, so many objects under them actually breaks container isolation. On the other hand, many applications need to access the objects under them. So you can see the conflict is here. So the container hosts really don't want containers to access some objects under them. But the containerized application sometimes needs to enter some objects under these file systems in order to function. So that's where the conflicts come from. So however, we notice that these conflicts are totally avoidable because a lot of the times, this host policy and the container policy are really coarse-grained. So if we can fine-tune these policies, we can avoid a large amount of these policy conflicts. For example, I don't really see a case where Firefox needs the arbitrary read access to anything under proc. And also, we can treat this problem from its root by avoid the sharing at all. So for example, there is a recent proposal called device namespace, which basically isolates the /dev. And also, we're looking at the directions of can we provide this multi-layer file system to conceal the sharing of the proc. So we measure the performance of the namespaces by measuring how much system call latency we're adding to the system call mediation process. So the thing I want to highlight here is that for a typical for a typical container deployment scenario, where you have a container cloud and the container runs on that cloud, so we only introduce about 0.7% latency overhead to the system call mediation. And for a atypical scenario, where you have more namespaces that you have to route the operation to, this overhead basically increases linearly. But we can avoid this by using some parallelism. The details is in paper. So we also measure the application performance when they are deployed in the container. So we want to measure the applications when we are deploying the application. We want to measure when we have both the application profile and the host profile in place, how much do we affect the application's performance? So we measured this web server throughput. The results we see is that we will almost have the same identical throughput for the web server with and without this application profile being enforced. The reason is twofold. First, the AppArmor isn't really mediating so many system calls from the web server. And second, the mediation only introduced about 0.7% overhead. And to summarize, so existing containers cannot really leverage kernel security frameworks to apply local security control. And a naive way of virtualization may break security offered by the security frameworks. And we designed this routing-based security namespace that preserves security while making kernel security frameworks available to containers. With that, I would like to thank you and welcome any questions.
Thank you for a nice talk.
Hi, John Criswell, University of Rochester. Interesting work. One question I have is that regarding your experiments, did you try a server where instead of having multiple clients, you just have one client? Because in our experiments on operating system kernel performance, oftentimes when running, say, a web server handling multiple connections, the overhead actually isn't all that much. But when we start running, say, a single server with a single client going as fast as possible, that's typically where we tend to see the overhead. So have you run, say, a server with just a single connection like SSH?
That's a great point. So we actually didn't include these results in the paper, but yes. So we didn't notice any difference between the latency of HTTP requests. I think it's because of the mediation cost is 0.7%. When it reflects in the application level, it's really hard to notice.
Okay. I also noticed that you showed the results for mmap. Are you seeing the same overheads for the other system calls like read, write, and file system and whatnot?
Right. Actually, So for the mmap and the read is very similar. For the write and exec, it's actually the performance overhead is actually even smaller because the system call itself takes a longer time to complete. So the added latency becomes an even smaller portion.
Okay, thank you.
Sure.
Hi, Cliff Schroders from Leeds Beckett University in the UK. Great work. So the examples that you gave, like IMA and AppArmor, don't conflict with each other. If you want to include something like SELinux, like you included in your early slides, it's going to be much more complicated. And do you think that's even possible?
Yeah, well, I was actually waiting for that question. So I have a backup slide. So we did a study in the paper. So trying to find if this approach is generalizable to the SELinux. We feel like this operation in large can be applied, but there are two specific challenges. The first is that SELinux involves file system labeling. So that means the subjects and objects will have multiple labels in this case. And that means multiple security attributes and runtime manipulation of security attributes without reboot. So based on our discussion with the kernel community, they don't like it.
No, I'd imagine not.
Right.
Because they also, if you've got multiple instances of SELinux or SELinux and AppArmor, they've got like different the data structures that they share, and even within the Linux security like kernel community, there was arguments of even whether or not you could have AppArmor and SELinux on the same machine,
right,
let alone multiple instances for each container.
Right.
But I think it's a really great idea. It's like there's just
really,
quite a lot of
it quickly
implementation.
becomes untractable. So it's I guess that's the reason. It's just too complex. So that kernel community feels like the simpler the better. So
I mean, one option would just be sticking with AppArmor for containers, and
yeah,
at least it's a simpler problem.
Yeah.
Yeah. Thank you.
Sure.
Thank you.